Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss approximating the integral using least squares best fitting polynomials. So in this topic we will discuss how to estimate an integral of data that is noisy by using the least squares best fitting polynomials. We will describe the formulas both for linear and quadratic polynomials, and we will discuss it for estimating the previous time interval, as well as extrapolating forward to determine what the integral may be over the next time interval. So as before, we have found the least squares best fitting linear polynomial that passes through n equally spaced points. All right. Well, if we wanted to integrate over that last time interval, so our last sample point is taken at the scaled and shifted point 0, that is the value y sub n, and we'd like to estimate the integral over this last time period. Well, all we have to really do is integrate that least squares best fitting linear polynomial on the interval from -1 to 1, and that gives us the expression a0 minus a1 over 2. And you can see that that is the average of the two y values when evaluated at when the least squares polynomial is evaluated at 0 and -1. Just one caveat. Remember that we scaled. So the original interval was of width h, and therefore we have to multiply this estimate of the height of the function by h. So this calculation best approximates the integral using a least squares best fitting linear polynomial. Similarly, we can project into the future. We can estimate what the integral will be over the next time interval. That is, we may want to predict how much energy will be used in the next time interval. Well, now we're just integrating from 0 to 1, giving us a slightly different expression. And as before, we must account for scaling. Similarly, given noisy data, we could find a least squares best fitting quadratic polynomial, and suppose we wanted to integrate that quadratic over the last time interval. That is, we'd like to estimate the area under the curve here. That's straightforward enough. We integrate that interpolating polynomial from -1 to 0. We multiply by h to deal with scaling, and that gives us the expression on the right-hand side. Similarly, we may want to project one time step into the future. For example, how much energy or how much current will pass or how much charge will pass over a period of time. In the next time interval, we would integrate into the future, and that could be done by integrating that least squares best fitting quadratic polynomial from 0 to 1, again multiplying by h to deal with the fact that we're scaling. All right, those are the two formulas. Following this topic, you now understand how to estimate an integral using the least squares best fitting polynomials. You're aware that we can both estimate the integral over the last time interval or extrapolate into the future and estimate the integral over the next time interval. And again, you should understand that if we already have the coefficients of the least squares best fitting polynomials, then we can find the estimates of these integrals in order 1 time. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!